Okay, just to kind of set the stage, a very standard kind of, or a very basic thing that happens in almost all computer vision tools and efforts today is you somehow convert images, and we'll talk a little bit also about videos, visual data into vectors. So that's sort of effectively a basic requirement for all modern machine learning techniques. It was not always the case. So initially, when people started thinking about how to make computers understand the visual world, they would think of largely handcrafted, created by people thinking hard, what is the right way to represent an image? People would present images as maps, as sketches, as various set of rules, predicates, which may or may not be true about images, etc. So not data which is kind of naturally numeric data. In the end, everything is numbers in the computer, but kind of from a human perspective, really there was fundamental mapping of images into this sort of other types of data. Gradually, it became more and more common to represent images with sets of numbers. So one of the early work by David Marr, who was the PhD advisor of our chairman of the board of trustees, Eric Grimson, kind of thought about representing things in the real 3D world by sets of parameters describing primitives approximating those things. For example, a person could be just a whole bunch of cylinders or prisms, and then you need to describe shapes and orientation of the things. You can describe human face by specifying where different landmarks, corners of the eyes, corners of the mouth, different parts of the nose and ears, etc., where they are relative to each other. All of those things naturally are a bunch of numbers. And so now you can think if I have a fixed set of those things, I can just arrange them into a vector. When machine learning really took off, which was early 2000s, the people said, well, if we want to run a linear classifier on images, we need images to be vectors, and the standard way to do that is to say I have an image, like the simplest way. If I have an image of size n by n pixels, I will just write down all the pixels in order, so I'll have a vector which is of length n square. Maybe if it's 3 colors per pixel, so it's 3 times n square. But that's kind of a very naive, in some sense, way of mapping it. And for many years, that was the standard, including most of my PhD, that was the standard way of mapping images into vectors. Many famous data sets and tasks, especially for where image classification in particular were entirely developed and saturated to a large degree using that kind of representation. Probably everybody has seen the MNIST digit classification data set. You may not have seen this COIL 20. It was the first, I think, large scale. It had 20 objects. It was large scale instead of 2 objects. Data set for object classification. Olivetti was one of the first widely used in research data sets for faces. I don't remember the size, but it's a few hundred faces. So all of these are examples of image classification. So it makes sense to convert images of a fixed size into vectors, train some sort of SVM or linear or some other linear classifier and classify them. Now, what I'm going to talk about today is how far we have kind of advanced beyond that. I will tell you a little bit more about the history, bringing us to what's typical today. Talk a little bit about modern tokenization efforts. I will talk about how these methods relate to how we map text into vectors. And as you have come to expect from me, there will be a rant on that topic included in that part. I'll talk a little bit in more detail about particular challenges and some solutions we have for embedding videos, which some of the challenges are compounded because videos are just much bigger things than images. And there I will focus on some recent work led by Chester and by Marcelo in that domain. And then towards the end, hopefully we'll have time, I want to talk a little bit about some ideas I'm trying to pursue with some collaborators and how we can do a better job and what I think is more correct way, a more promising way to represent visual data than what we do today, trying to address some of the challenges. All right. So I should say that all of the work I will be mentioning specifically beyond, when I talk about our recent work is joined with Chester, Xiaodan, Marcelo, Karen, Shiri, and our collaborators, and Alex Liu at MIT, Fabian Kava, and Brian Russell and Joseph Civic at Adobe, and recently Alyosha, who Berkeley and also is helping Adobe join this. So, all right. So, what can we do beyond just writing sets of pixels as vectors? So one of the early work which went beyond just writing the pixels was actually work by our president, our current president, Matthew Turk, not by Trump. And I'm not aware of this work. And the idea here is that you actually, essentially it's still representing an n pixel image as an n squared numbers, but now you actually change the basis. And for example, you can do it by finding directions where there's meaningful variation that you care about, for example, variation between different people, and then kind of find eigenspace of the transformation and becomes something called eigenfaces, was very famous. And the idea is that you can now represent each image as a linear combination of the basis vectors in that space. So now instead of mapping this image into n square long vector, you can actually, in this case, maybe map it into 12 numbers, which is just the coefficients for the important dimensions in that space, and could be important in general explaining the variance, could be important for a particular classification task, etc. So that people did that for a few years, that kind of stuff. There's a lot of course, subsequent work refining it and improving it. Then the dominant paradigm became taking an image and saying, well, especially as we work with bigger and bigger images and more diverse images, different tasks, different kinds of things, if people realize that it seems to no longer make sense to present an image as a single vector, and instead they moved to representing images as sets or bags of vectors, and these vectors now came from what is called feature descriptors. So the idea was you try to look for some interesting points in the image. There's a huge, I would say, cottage industry, actually was beyond cottage, it was really big industry, on how to find those places which are important and how to extract vectors representing them. And already at that point, everybody wanted vectors because everybody wanted to use machine learning, which at the time primarily was still some kind of linear classifier or something similar to that. And initially, it was assumed that you have to do this interest point operators. SIFT was probably the most famous example, which is one of the many kind of ways to describe image points, which emerged as the winner in the sense that it seemed to be really robust, really general, and it's actually still in use today in many applications. I will get into that, but it has not been completely supplanted by deep learning in a sense, because deep learning is done on top of SIFT descriptors. The SIFT descriptors are still important. And initially, so people, there's interest point operators, and then as people move towards even bigger data sets, bigger images, etc., there was kind of an amazing discovery that you actually don't need interest point operators. You can simply extract things from a grid, a dense grid of points, and the main issue is that just more points than your interest operator would have found. But if you have enough compute, which always proves, it turns out to be okay. And so just a second. So you can represent an image as a back of the descriptors. You can do all kinds of things on top of that, in some sense similar to eigenfaces. You can say, I will take these descriptors, I will cluster them, and now I will assign every point in the image to one of those clusters. And now my vector will be the histogram over different types of features. And that's a new vector instead of the original bag of vectors. Yes?
Was it necessarily true for eigenfaces that each basis vector itself kind of had a visual representation or sort of?
So when you say visual representation, was it interpretable?
Yeah.
And the answer is generally not necessarily. And there was a lot of work trying to see if you can find better representation which are interpretable, or if you can guide them, but not a priori. No. A typical thing someone would look and say, oh, we can interpret because out of the 5 top vectors, this one means age, and this one means ethnicity, and this one means lighting, and the other 2 we don't know how to interpret, so we'll ignore it. So, all right, so then people figured, well, it's still a kind of impoverished representation because I just extract things everywhere. I can do even more sophisticated stuff. I can, for example, extract different features and cluster them, but do it at different resolutions. So I can give a histogram of types of descriptors after clustering for a whole image, for different quadrants of the image, quadrants of the quadrants. This is known as feature pyramid. This was a very influential work by our adjunct faculty, Lana Lazebnik, who is a professor at UIUC. It was probably the dominant approach for a few years. They got the Test of Time award for this work 10 years later. And again, initially the points would be extracted from some important locations, and eventually people started doing it just for dense grids. And then I'm not going to talk about convnets. I figure not everybody knows this history. Everybody probably knows about convolutional networks. Convolutional networks is another way to map an image into a tensor or a vector depending on how you want to do it. Typically, you have in the end of ConvNet, you have eventually a vector, which you do things like classification. So, and of course, ConvNets were also dominant for a while, but nothing lasts forever. And so now we have, arguably, and I don't want to argue about that, so we have transformers which have become, I think, certainly most widely used, even if that's necessarily it's not clear if they're actually better than ConvNets, but most widely used types of image processing. So let me just go briefly through the details of how VIT, vision transformers, work, because it will be kind of a little bit more relevant. So the idea is you start to partitioning an image into patches of fixed size, and how many patches, how big they are, is kind of determined largely by how much compute you can afford. And the intuition here is the smaller your patches, the more of them you will have at a particular resolution of the image, the more compute transformers will need. You represent these patches somehow into vectors, and that is done either like the old school, like in the very first slide, you just can arrange the pixel colors into a big vector, or maybe you learn some linear projection, or if you want, you put a little convnet there which maps to a vector. And eventually, all of those vectors get augmented by positional encoding, because transformers otherwise have no idea where things are coming from. They don't know the notion of spatial location. But you reintroduce it, run this thing through some number of transformer layers. Eventually, you get, for every original position, you get an output vector. But what's important for a lot of applications is not any of those, but an extra position. You can think of it as like additional position outside of the image, which is called originally class token, because if you're doing classification with this, then that's what you'll be classifying. And this thing kind of interacts with all of you can think of it as a vector representing the task. And that interacts with all of the positions of the image. And eventually, the output of that on the transformer is what you classify with, however you want to do it. So one unfortunate thing here is that now when I say tokens, what does it mean? So it turns out that there is a little bit of a confusion, in my opinion, very unfortunate, about terminology. So let me kind of tell you what I understand these different terms to mean. So embedding, which is the title of my talk, it just means mapping something, which is some object, into a vector. And vector here, we can quibble whether it should be a tensor, but I think most of the time we can just think of it as a vector of fixed size. So that's the operation which maps something which is not a vector, non-naturally into a vector. Tokenization, for me, is the process of taking input and breaking it down into elements. So, and we'll talk in a moment a little bit about text tokenization. There you have a string of characters or bytes, and you figure out where the boundaries are, right? If you take an image, you can say tokenization is partitioning an image into patches. That's tokenization. There is also a notion of quantization, which we'll talk about now next, which is representing things as discrete, as indices into some set. So indices into some sets are basically symbols. They're usually numbers, because you need to, that's how you indicate which element in the set you're talking about, but they're really symbols. They don't have the numbers are not meaningful as numbers. And so usually in a lot of the stuff in vision, as we'll see, the way you go from these tokens embedded into vectors into quantized representation is just do clustering. I mean, K means clustering, known in a fancier way as vector quantization. So if you do that, then basically if you have a vector and a code book, a set of vectors, you essentially associate each of those vectors with the code element of the code book which is closest to it, and then its index becomes the discrete token associated with that vector. And people also talk about discretization. I have no idea what that means. I think it means the same thing as quantization. But yes.
Just to point out the terminology, if you're talking about large language models, the word token is a discrete thing.
I disagree. I think that's because
if you say
so the first thing that happens in a lot, not all now, but a lot of big LLMs is you run BPE. BPE is a tokenizer. That's tokenizer in my sense. It takes the characters and figures out where the boundaries are. Those things are embedded into vectors, right?
But conceptually, I think of it as an alphabet.
But before, so
I understand what you're saying.
Yes. So the alphabet in modern LLMs are not actually the alphabet, right? It's alphabet which is optimized, and that process is what determines the tokens. Once you have the tokens, of course, you can you can assign them. Now in text, so let's talk about text in a second, but just to point out why is it important to have this distinction between discrete and real valued, and I welcome dissent. So I think in general we want a vector with real valued vector most of the time, but a lot of people really in various domains really want discrete representations. Why do they want discrete representations? Well, what's good about real valued vectors? This I actually had this, if those of you who were here from talk earlier may have seen this image. I independently had it started last night. So the idea is that you want to do some kind of linear algebra, roughly speaking, on your representations. You will pass them through a whole bunch of linear projections and matrix vector products and whatnot. You need real valued vectors for that. What's good about discrete representations? I think there are basically three things. They are considered to be easier to learn. I think it's true. Because roughly speaking, it's easier to learn to distinguish between a fixed set of possibilities than to kind of think of regression, real valued outputs. For example, because losses are easier to do, the model is clear, you just have softmax is a natural way to represent classification, whereas if you have regression, then what do you do? If you just do least squares, it effectively means that you assume a single Gaussian. It kind of gets complicated if you want likelihood from that. Discrete representations provide compression in a very kind of pragmatic sense, right? We need fewer bits to represent things if it's just a set of 4,000 possibilities than real valued vectors. And maybe interpretability. I put a question mark here. I'm not 100% sure why it is more interpretable. There is some argument that people are good at understanding. If you have complex data, it's easier to understand in a symbolic way. You can understand in a visual way, but if you have high dimensional data, it becomes really hard to visualize, but writing down symbols becomes a lot easier maybe to kind of track what's going on there. Maybe.
Yes, even though the tokens are optimized in language, many of those tokens are just words. And they're
right.
So interpretability.
So many are words. So this is an example. This is a tokenizer from GPT everybody has to have an example of GPT. I can't bring myself to produce the stuff that GPT writes, so I just have a tokenization. I have a tokenization, it goes to YouTube, right? I have a tokenization example from GPT-4o. So this is the actual tokenizer that it has. So this is an example sentence to test tokenization. I'm using it in TTIC on embeddings, wowzers. So you can see how you're right that most of these things are words. Not all of them are words. I should also say that this is English, and if you try it in other languages, it becomes often, especially lower represented languages, it often falls back on things which are much closer to small n-grams, or even just individual characters, or even individual Unicode bytes. So the bottom line is it's a mix of those things. So in text, this tokenization is very kind of natural, and you can say that the exact boundaries maybe are important, but there's no question that there is some point from which you start. Right? You start with individual characters or bytes. There's nothing less than that. Text, it's a natural way of representing text. BPE, I don't want to get into the details, but basically BPE tokenizer tries to optimize. It's sort of a, those of you are not familiar with this, but are familiar with Huffman coding, I think it's a similar idea. You're trying to find a way to encode your text by encoding more frequent things as a single, if possible, as a single element or no, just a handful of elements, so that it leads to compression. Compression is not doesn't directly optimize compression, but basically it does that. And then once you do that, it's important to remember that in the end, when you're going to work with these tokens in an actual modern machine learning system, you're not going to work with indices. You're going to work with vectors. So you still have to have this codebook which maps each of those tokens into an embedding. And that's usually optimized together with everything else. In the very early kind of stages when people started to get this kind of stuff to work, there was a period where you would independently optimize the vectors using something like word2vec, which is its own objective, and then fine-tune them maybe as part of an end-to-end training of a language model for things like translation or prediction of tokens or whatnot. So, okay, so that's text. Okay. So once this became very successful in language, people started saying, well, let's see if we can do something similar in images. So how can we do it in images? One of the first efforts was VQBAE. I'm going to briefly tell you about some of these papers, which I think are influential, or at least to me, they're influential in how I think about this. So VQV is a generative model, and you will see that there are going to be a few generative models. And all of the stuff I was talking until now about vision was about recognition and stuff like that. So it's interesting. Keep that in mind. So, so the idea here is that you have some kind of encoder which takes image patches, still embeds them into vectors. Those vectors are snapped to, using a codebook, to discrete tokens. And then those tokens are expanded back into real valued vectors, but now you only, let's say your codebook size is 4,000, you only can have 4,000 different real valued vectors. So you populate this tensor back with those, and then you train a decoder which from that reconstructs back your image. And if you do it this way, then you get fundamentally a tokenizer here. So you can take an image, run it through the thing, using the codebook, convert every image patch to an integer, and now you have a discrete representation. I don't think people found those representations to be super useful for tasks other than generating images in this framework. I should also say that it was really tricky for them to get this to work. How do they get this to work? It's important. So you can't just say, I will learn this embedding and then later I will do the codebook, because it relies on having the codebook when you decode. And so you have to somehow simultaneously learn the embedding part and the codebook, and that requires, if you just do it naively, they kind of tend to chase each other. You can write gradient descent for everything, but it will basically just, the codebook will update itself and the embedding will update itself, and often it will be opposite direction. And so you have to do all kinds of tricks, like stopping the gradient and changing the learning rate so that one goes much slower than the other. And it sort of works. There was a subsequent version which made better images, where you do the same thing but at multiple, basically 2 different resolutions. So I think the interesting thing here is that it has this kind of afterthought quantization, which apparently helps. And the main reason they wanted to do it is that if you want to generate, I'm not going to get into details here of generation, but if you want to generate an image now, first thing you need to do is generate this matrix of integers. And it turns out it's a lot easier to do with various models than generating real valued vectors. So that makes sense, and that was kind of inspired to some degree, I think, by progress in language. Here's another model called VQ-VIT GAN. I'm curious, who has heard of VQ-VIT GANs? Right. So this is actually, contrary to popular belief, I'm happy to hear if someone strongly disagrees, this is an alternative way to generate images, an autoregressive model for image generation. And I am not aware of any convincing evidence that it's any worse than diffusion models. And in case you care about that kind of thing, this also is from Google, so they have the street cred. So for various reasons, diffusion models captured the public imagination, but I think this is perfectly fine generation model. How does this work? Again, you have an image, you partition it into tokens, into patches, which are, I think, of tokens. And then you learn, similar to VQV, kind of, you learn an encoder-decoder architecture, which is forced to go through discretization. So you can learn simultaneously using similar tricks as VQV. You learn the codebook together with an embedding for encoder and the decoder, and you learn to represent images. And once you have done that, the next stage is you actually learn a transformer, autoregressive transformer, just like in language. You can say now it's basically kind of like language. I just have maybe 4,096 words, which are integers here. I will just learn to predict, I go through the image in raster order, and I predict, I can mask some of them, predict them back, and however we want to do it, there's a variety of ways we have tried to improve upon this further. So the idea is that you basically learn this using the successful techniques from language, because now this is kind of like language because of the tokenization of the patches and discretization using clustering. Question, yes?
The positioning is 2D, right? It's
the positioning where? The position encoding?
Yeah.
Well, yes, except that if your image is fixed size, that is not meaningful. You just enumerate things.
But how much is that sequential information important for generation?
Oh, it's very important.
I thought, okay, like does it have to be sequential or can it be like?
I'm not sure what you mean. You need to know which token came at which position if you want to reconstruct the image. That makes sense, right?
Yeah.
Therefore, it also makes sense that you need to know where, if you're predicting a token, you need to know where it is.
Yeah,
when you're generating it.
I see, but I was wondering like what, I guess it doesn't matter like how you sequence, how you.
As long as this enumeration is, those are again, those things are converted into numbers using various, whatever people like to do, Fourier features, whatever. But in the end, they just indicate positioning. As long as it's consistent in all of your training and in how you deploy it, I think it's fine. You can start in the center and go in a spiral. You can start in a raster order. You can have a random permutation. I think it will all work fine.
See, I was wondering, like, if you first construct people's faces, then you construct everyone's.
So that's, I think we will get to that. You are saying that some things are more important, and I don't think this works like that.
I see.
All right. So again, observation, these are discrete tokens which are done after you quantize embedding vectors. Associate with image patches. So again, tokenization is kind of arbitrary and fixed. You have to train things with reconstruction objective, and your goal is generation. So why does it make sense to borrow ideas from language, and what's different and similar between images and text? And so a very common very common direction in vision research for many years has been that we should really think of images as text. One of the very first papers I think I saw at the conference, my first ICCV 2001, was a paper which was very influential at the time called Image Understanding as Machine Translation. I should probably have a figure here. And the idea was that images really are documents and image regions are words, and we should just learn to translate from that visual language into English. And David is happy, of course. An important thing is how do you find the boundaries, and back at this, there was simpler times they only had to get it to work on like 3 images, and so somehow segmentation worked. But basic idea is that, well, and David, I think that's why David was like, thumbs up, our understanding of the world is fundamentally symbolic, and so everything should be converted into symbols. I'm slightly oversimplifying, this is a rhetorical effect. And so it makes sense to kind of do this and attempt to do it this way. Now, I claim that there's a huge difference between images and text. And by the way, I try to insist on calling these models text models when I can, and within reason, hopefully. Because really what these LLMs today are trained on is a huge fraction of that, probably majority of the bytes I've seen are not actually human language. They're text of various other kinds, programs, documents, I think binary files, which is great, which is why they can do all the stuff which actually is useful. But however, any text has big difference between images and with images. So first of all, text is something which is fundamentally created by humans. It's symbolic, its nature is symbolic, it's natively symbolic, I would say. You can convert it back on your right, you convert the symbols back into real valued things, but in our brain is very good at deciphering it. That's like OCR that you do when you read. But actual things represented that are symbolic. The symbols are the natural form of that. Images are made by nature. Some images are made by people, but let's think about photographs just. But I'm happy to offline discuss how it's true even for things like art. But images are made by nature. They're kind of naturally real valued, and please don't start arguing with me about pixels, RGB being 256 possible values. Images are really kind of real valued. They don't necessarily represent symbols. More important is there is kind of variability, inherent variation in images which doesn't exist in text. A symbol always means the same thing, which is what makes it a symbol. It doesn't matter how it's represented. It's the same symbol. A pixel in the image does not always mean the same thing. And this is one of the figures I use in my class when I talk about lenses and how telephoto lens. But if you just look at it, hopefully you can see what's in these images. These images show as you kind of zoom in, and not in just a traditional telephoto lens zoom in into the scene. And you see the same if you just look at the stern of that boat. As you zoom in more and more, it comes closer and closer to you. And what before was a single pixel turns out actually corresponds maybe to a whole big section of that boat with an anchor and everything else. And so that's just one example of how the same pixel in the same image might mean different things. There is a nature of multiple scales, and that just doesn't really exist in the same way in text. There are some other kinds of scale, this paragraph document, but not in the same way. A byte in your text file always means the same thing. And I think that makes the tokenization goals in text are fundamentally different from tokenization goals in images. And in particular, when people discovered that you can actually give up the BPE encoder, and some of the fairly successful models today do not use that and directly operate on bytes, I don't know, some people were shocked. I was not shocked because, yeah, that makes sense. Those are actual atoms of text, and if you have enough data, enough representation power, why wouldn't you be able to do that? But with images, I don't believe we'll ever get to the point you will just represent pixels as atoms, because pixels are not a meaningful thing. So I think it requires something else, and much more important to learn tokenization here. And again, tokenization in the sense that I use, which is how do you decide what elements is your input composed of, and how to extract features from them. All right. I think in the interest of time, I'll try to maybe go a little shallower in some of this stuff. So I will just mention, there's another way to represent images as a set of discrete tokens. This is primarily I'm mentioning because I think it's something that we're actually using in one of our work we'll talk about next. This is called TTIC. You can see it's kind of similar to TikTok because it's done by people at ByteDance, which is a company that still, I believe, owns TikTok. And the idea here is that you, again, learn to reconstruct things, but now instead of learning embeddings and running some kind of DQ on top of them, you kind of incorporate quantization in this step when you embed vectors, and you learn to reconstruct images from a set of discrete tokens, but these tokens are no longer associated with image patches. And VIT paper, I wish people stopped with those titles, said the title was "An image is worth 16 times 16 words," and the title of this paper is "The image is worth 32 tokens." And of course, that's not true, but the point is that you can actually learn to map an image into 32 integers, which index into a code book of something like 4,000 possible real-valued vectors, and that allows you to reconstruct the images fairly well. And you also can do things, you can generate images, of course, and to some degree, it turns out you can do things like classification, although it seems like less successful. But that's the kind of basically newest iteration, it's from last year, of this idea of turning an image into a set of symbols which are interpreted for things like reconstruction. So why do we keep talking about reconstruction? I won't spend too much time on this. I think that the main reason really is that this is, first of all, what a lot of people want to do. You go to computer vision conferences these days, I think that at least 50% of the papers there are about image generation, probably more than 50% at this point. It's a good way to, if you can train whatever you're training with the image reconstruction objective, it's a very good objective because you just need a lot of images and a lot of compute. Who doesn't have a lot of compute? I guess we don't have a compute, but basically you can say, okay, I just will throw a huge data set. I don't need any labels. I don't need any fancy loss. I'll just try to reconstruct the pixels, and if you can learn with that, that's very appealing. And of course, there is a story that if you learn to generate images in a way which is reliable, so that you know what will come out, controlled, so you can tell it what to generate exactly the thing you want, and if you can do that, then somehow you must have unlocked the secret of visual perception as well, because if you can create it, then you must be able to invert it somehow. People say vision is inverse graphics, and it has not panned out, in my opinion, for any of these methods. But I know Michael is working on that, and hopefully others agree me, and hopefully it will. But as of now, it hasn't. But anyway, that's why all of the stuff you are seeing here is generation related. So what is, if you want to represent video, what can you do? So one thing you can do is just to say, what is a video? Just a sequence of images. I will represent each image in any of the ways I've described so far, and that will be good. So one big problem there is that it's still a lot of stuff, right? So if you want to work with long videos, and a very common type of video until recently in computer vision was, let's take a video of 16 frames. And when people talk about long videos, it's maybe a minute. And very few things actually work on that. But some of the tasks I will tell you, a minute is on the short side sometimes, and we often want to think about videos which are tens of minutes or even hours. And things just start adding up. If you have a bunch of vectors for every frame, and you have tens and hundreds of thousands of vectors, it just becomes very difficult to ingest in your method. So On the other hand, you can say, well, a video is just like a special kind of four-dimensional image. And if I want to just, let's say, classify a video, I just need to embed the whole video into a vector. And a common type of task for it is something called action classification. So these are examples from very kind of one of the first widely used data sets for that called UCF 101, the 101 types of human activities. And you need to classify, and I should have hidden the title here, but you can see how this is a video of a makeup application playing the doll, I guess is a drum, baby crawling, shaving beard, right? Makes sense. But if I've hidden those titles, you would still know what's going on here. So it turns out that if you actually want to classify those activities, someone after many years of that data set being out there attempted this baseline. What if I just take one random frame? And it turns out we get almost the same accuracy because really you don't need to see the video. So if you do something like that, you don't really lose that much from embedding the whole video. Maybe you get a little bit of extra. For example, if there is one activity sitting down in the chair, another getting up from the chair, and you have just one frame in the middle, then it's hard to tell, maybe. And if you have the whole video, you can kind of embed the general direction, right, down or up. But generally speaking, this is a pretty impoverished representation. And the tasks I'm going to tell you next about are actually focused on a much finer grained understanding of what's happening in video. And so the first task I'll talk about, and those of you who were at the student workshop have seen some of this work, but I think everybody here, unfortunately, was at the student workshop, so it will be new to some of you. So one task is sign language understanding. Sign language is a language that deaf people natively use to communicate. There are hundreds of sign languages around the world. These are not just a way to gesture your emotions, as some people say, and this is not some way to just gesture English, for example. American Sign Language has very little relationship to English, generally speaking. It's its own separate language with its own morphology, syntax, lexicon, etc. Many sign languages, of course, have some borrowed elements from the local language, especially when you do something called finger spanning, which is indicating words for which there is no standard sign, names, abbreviations, etc. But generally speaking, it's a language. And so a task of translating from sign language to English is basically it's a translation task. Can you translate from one language represented by video to another language represented by symbols? So this is an interesting question, right? This is in some ways similar to spoken language. This is a language which, spoken language, if there is a written form, I think you can say that it's kind of like OCR. You say things, but you could also write them. And what you are saying, you could read it off, and basically there's the true underlying content is symbolic. With sign language, maybe you can say that, and we have Serpil here who is a linguist of sign language, but I think, for example, it is not agreed upon among the people studying it what the symbols are, right? So we think that they're symbols, but it's not clear. So it's a little bit more in that sense like a classic computer vision problem, understanding sign language. But of course, in the end, the target language, English, is symbolic, so you just need to translate it using some sort of language model which spits out good English, but how do you represent the video? So I won't show you the example video, but you can imagine that the person is speaking with sign language without, it's entirely visual. And so Chester has been leading work on this and has done a couple of interesting things. So one of them, the first effort, together with Shaudan, here is something called Sign Musketeers. It's because they're going to have four musketeers, three musketeers, but actually four of them, right? D'Artagnan is the fourth. And so here you have the three musketeers are features extracted from the face and the two hands. How do you find those things? He used off-the-shelf pose estimation, which at this point is good enough to fairly robustly find where the face and hands are, but not robust enough to actually give you the shape of the hand. It really messes it up a lot. And so you do need to go back to the pixels there. And the fourth, I suppose that's the D'Artagnan, is the body pose for the upper body, which basically tells you coarsely where are the shoulders, elbows, and wrists. And again, the pose estimation models are good enough for that. And then you map each of those things to a vector. And the details are not, I think, super important. You do it by fine-tuning some standard representations for embedding images. Dino, right, is yet another image in vector out. But now you do it for those pieces of the original image that you have focused on. And you focused on those because you assume, from what we know about sign language, that face and hands are going to be important. and we assume that the rest of the body pose is important as well, but we don't need to see the pixels there, because we need to know where those joints are. And now you combine all of that into one big vector, that becomes the single vector for the whole frame, and then you feed that into your favorite transformer, which learns to adapt to these vectors instead of standard text vectors, and then spits out the English translation. Any questions? Okay. So interesting observation here is that now the tokenization, again in my sense, is this first thing where you kind of use a pose estimation kind of to tell you where to look. And of course, it's entirely tailored to this task. You can imagine that, and I think Chester is thinking about extending it to other tasks, which involve looking at people. But if you want to understand a video of, a flowing waterfall, that's not going to help you. So you need something else. But that's kind of task-specific. You can think of task-specific tokenization. Another observation here is that once you extract those tokens, you really couldn't care less what's happening in the other parts of the image. What's happening in the bookshelves of this person is completely irrelevant. So you don't need to extract any information there. And you still extract a single vector per frame. But this vector is, you never need to read in all of the frames at once. You can read one frame at a time, map them to this vector, keep the vector, go to the next frame. So it allows you to ingest much bigger videos, still limited to maybe a few hundreds or a few thousands of frames on the typical GPU we have, but bigger than what you could do before. So subsequent work, which is, I think, cooler, again led by Chester, now we say, okay, we still keep those four musketeers, the hands and face, upper body pose, but now we are going to mix them all immediately into a transformer, and transformer is a temporal transformer. And because, again, you don't need to keep every frame. You extract the features from the frame, write them down. You can do it for the video, you pre-process it, and then run transformer. Transformer now, each frame has those four vectors representing it. You put all of them for the entire sequence, input in the transformer, and the transformer eventually outputs something, and that something that it outputs can be directly fed into the transformer for the language model, which again has to adapt to seeing those things instead of input text, but basically it's like a translation task. So the important thing is that to train this, what we do is go back to the idea of quantization. You run k-means on these tokens for face, for hands, for upper body pose, different, each of them has its own dictionary. At the moment, you learn the indices, so now you have, let's say, 512 possible types of hand shape, 512 possible types of face, etc. And you learn to predict masked identity of those discrete tokens for masked elements of the input. You randomly mask face features in one frame, hands feature in another frame, and then you put it all in the transformer as masked token instead of real features there, and then the output should, you're not trying to directly predict the pixels or even the features, you just want to know which of the 512 types of a hand shape was in that position. Yes?
Do you only classify, do you only take 3 patches as inputs?
3?
Yeah, the face,
There are 3 patches, face and 2 hands, and there's a small vector representing the body pose. That's right. Nothing else. So the basic idea is kind of like the previous slide, but now you use them in a much more sophisticated way. I won't get into the details of some details on top of this and how well it works. This is just was accepted as an ACL paper this year, and the assignment here is the ACL findings. We found a conference which will accept it, but I should tell you, basically this turns out that once you pre-train in this way, and that's completely self-supervised, right? You just need videos, ideally of sign language, and then you fine-tune it for some tasks, and for some things you can even use the zero shot just to translate. And for many tasks, it achieves state-of-the-art results. Basically, I don't like doing that, but we call it the foundation model for sign language. So because it's a model which is pre-trained in a self-supervised way and then used to good effect on a variety of downstream tasks related to sign language. All right. So another piece of work I want to tell you about, which is again related to understanding videos, is movie editing. That's something that Marcelo is leading. And just to, when we talk about editing here, I don't mean changing the pixels. I mean what movie editors do, and some of you might not have thought about this, there is a lot of footage that is filmed. Apparently, I learned it from myself. I didn't know. In a typical high-budget, Hollywood movie, the amount of footage which is filmed could be more than 1,000 times more than the actual length of the movie eventually. If you 2-hour movie, you could easily have multiple thousands of hours filmed. And it includes many, many takes, many different cameras. Sometimes it's multiplied by different attempts to do some special effects, etc. And so now you need to decide where to splice and cut and assemble that footage into a movie. So this is an example of a little bit of a movie where you will see that there is going to be, you see that? And this is again, so there's 3 different shots here. So a shot is a continuous, something which will film continuously, and then there's a cut between them, right? And back, doesn't anyone know why it's called a cut? I'm sorry if I'm like that. I never, like is it, at this point, is it a ridiculous thing to ask because everybody knows, because nobody knows, I don't know. So I went back when it was actual film. Sometimes it's still, apparently, I think still in the majority of films, it's a lot more and more digital. You would find the right place, cut it, and then splice it together with special glue, and that would become so here's another one. This one I think is high times enrichment height. And so you will see that there are multiple shots, a second shot, and the idea is that it's not just random, right? How the shots are assembled depends on, of course, the story you want to tell. There are various rules which determine what is reasonable edit and what is not, and sometimes what is a great edit, what is not. Some of this have to do with aesthetics. Some of this have to do with conventions and styles, something which, apparently the editing conventions in Bollywood are drastically different from Hollywood movies, and Hollywood movies have evolved over the years and depends even on the style, etc. But the idea is that there are kind of rules. It's essentially a language. And in fact, people have thought for many decades about the language of filmmaking. A lot of French theorists of semiotics have written books about it. And it has to do with things which are kind of logically consistent. If a person runs, and then jumps from the roof and lands, it doesn't make sense to reverse those things most of the time. Some of the things, maybe you kind of show someone's face and the birds are flying and then their face again. You could do it in any other way, but it conveys particular emotion and feeling, and some people do it well, some people do it badly. And so we wanted to build a model which would do this. It's actually something useful for movie editors. We talked recently to an editor, is Pixar. With all of that, they spend a huge amount of time doing trying to find potential edits which are good, and then humans, senior editors look at those. And so, as with every technology like this, I'm concerned about putting people out of work, but at the same time, these editors thought that it would be really great if we could help people to do this. Eventually, you still need human judgment. So Marcelo has been working on this since last summer. We have a SIGGRAPH paper together with our Adobe colleagues, which is different from what I'm going to tell you in a second, but we are continuing working on this, and now we have Alyosha and Shiri have joined us. So this idea of representing the entire video or even the entire shot as a single vector just doesn't work here, because often a difference between 2 cuts, one great and one horrible, is a single frame. It's hard to believe, and I should probably have brought examples, but you really can see that in certainly a few frames could make a huge difference most of the time. And so you really need some embedding, which is a frame level embedding, because you need this temporal resolution. And so what we do is going to embed each frame, but we do need to do it efficiently, and that's again where the discrete tokenization comes in. And specifically, we for now are using TTIC. And the idea is that you have an example, positive example, something which was edited by a professional editor. You find it's very easy to automatically decompose it back into shots. Shot detection is basic. Cut detection is very well solved, and you extract tokens for all the frames of all of these cuts, and eventually your goal is to predict correctly the sequence, which is all the tokens of the first shot, then a special cut token, then second shot, etc. So it's a language model. The language now is a language of video frames and editing, because cut token is very important. If you don't use it, if you just say, I will just want to predict the sequence of video frames, everything falls apart and becomes, on every task we try, it basically gives you random performance. So now you have this, you just train an autoregressive model. We have a pretty large context. Because everything is discrete, it's fairly easy to fit very large context. We're using 128,000 token context for this model, and we train it just as autoregressive token prediction task on about 200 hours of video. Now we have a model trained on 8,000, which does better. And just sometimes it fails, but generally it actually achieves either state of the art or close to state of the art performance on a variety of tasks, which I want to get into because time is getting short and they're not super important. There's a standard benchmark for this called anatomy of video editing. Sometimes you really want to just rearrange the shots. It's one task. You can predict what will be the next shot given the previous few shots, and you have given a set of possibilities, what comes next. There is predicting various properties, is it going to be a close-up or not? And so on all of those tasks, we do fairly well compared to previous existing work, which was all trained in a supervised way on ground truth labels for a lot of those things. We just fed it a bunch of video and asked it to predict the next tokens of the next frame. So this is just an example of a failure. And just to give you an idea what's a bad edit, here's our 3 shots again. So this doesn't make any sense. They show one guy, Harrison Ford. Now there's 2 other actors, and he's talking to him, and then Harrison Ford is going to stand up and walk, but instead of this actor, in fact, I think the Fox is going to walk, and he's talking to him, and we see some other guy. It kind of makes no sense, right? So often, and there's another one which is similar, like it's along the lines of a person falls before being shot or whatever. So it doesn't always work, but it works much better than random, and again, close to state of the art. So this is good. Some observations before we talk about what's next. So all of this kind of embeddings, including the ones we are using here, with the exception of Schester's thing, are optimized for reconstruction and generation. So Schester's embeddings, the Schester and Chaudan's embeddings on the Shine Musketeers and Schubert are not optimized for reconstruction. They are kind of optimized for something else, not directly the task downstream, but something which is different from reconstruction, because we don't care about reconstruction. In neither of these tasks, we really care about predicting pixels. So it's not clear why we should be modeling that. In videos, the tokenization we use right now is extremely redundant. More than 60% of the tokens in a frame are the same as tokens in the previous frame, on average. So, and that's not surprising because a lot of the time there's not that much that changes. So that problem is also present in things like Schubert. You have this cluster IDs for different types of features. They are the same often for many, many frames that repeat after frame after frame. So in the movie editing project, we're trying to extract information from the whole frame. We're not focusing anywhere, even though probably there's only a handful of things that matter. A lot of them have people moving around. You don't need to see the foliage behind them to know what's a good edit, but we extract information from everywhere. In Schubert, we don't do that, right? We extract information from relevant things, but it's handcrafted, so it's not clear how to immediately extend it to something which is not about people moving their body. So the good thing about Schubert, right, what we do want to preserve is that it focuses. So now, what do I mean by focus? I have 4 minutes. Let's see if we can do it. So human vision uses something called foveation. I don't know if you've seen pictures like this, but our field of view, we have a retina, right, which has a set of receptors. In the point where you're focusing, where you're looking, kind of direction of your gaze, there's drastically higher density of those receptors, which can capture visual information, called the cones, than everywhere else around it, and falls off very quickly. So your vision really is kind of like this, and everybody probably knows this just by thinking. Like your peripheral vision, which is very coarse, you see, it's not like you don't see stuff there, you see it's like motion, but then where you are focusing, if your vision is good, you actually can see a very high degree of detail. And to scan the entire scene, people use something called saccadic motion, so your eyes can move very rapidly when you scan. I don't know if you know this, my students have heard it many times. Our eyes can move only in 2 possible ways, either quickly from place to place, it's called saccades, it's about 100 milliseconds for a typical person, or if you follow your finger, it can move smoothly, but you cannot do it without following something. It's called smooth pursuit. If you try to move your eyes, don't do that because you might harm yourself. Try to force yourself to move your eyes smoothly. Either you will think it's smooth, but actually will jump, or you will, feel a big headache. Only people with major disorders of the visual system can do it. So because we know that the saccades are kind of how people scan the scene, we can actually study it. we can understand how people do it. There's famous results by a guy named Yarbus from Soviet Union who studied how people scan. In this case, it's a painting by a Russian painter, Repin. And it turns out that very reliably, depending on what you ask people to do with this painting, their eyes scan very different pattern. You can say, just look at the painting. You can say, tell me how well off this family is. You can say, tell me what are the ages of the people. And if you do that, then people must look at faces. If you ask about material circumstances, they look at what kind of stuff is on the walls, and what the furniture is like. If you ask them this is interesting, estimate how long the visitor has been away from the family. They keep going back and forth. They're trying to figure out emotion, the eyes, what do these people feeling, right? Occasionally look at something else, but mostly that. So all of that is task dependent. There's a lot of work on something called visual search, where typically you show the person this picture of a table, and you ask them find a fork and knife, and you ask them first to fixate here. You make sure that they're looking there with an eye tracker. Then you show the image. Very quickly, typically they go here, and then they go here, and then they go there. And within 2 or 3 or 4 steps in this image like this, they find the fork and knife. So how do they do that? There's peripheral vision. There is some context from they're looking, but basically, peripheral vision tells them that maybe it's worth looking there. And so they go towards there and explore the image in this way. People have tried doing this in computer vision. This is a paper by Antonio Cutralba, who did this a few weeks ago, and colleagues. The idea is that if you know that you're estimating the human gaze, maybe you will emphasize, you'll actually distort the image so the eyes you have higher resolution on the eyes. And if you're instead trying to classify a bird species, maybe you will look at bird's beak and wings because that's important. And you learn to do that, but each task requires learning a different pattern of distortion here. People have tried doing this in various other ways. I really am out of time, so I will just say that there is a small number of papers compared to the thousands of papers on computer vision in recent years trying to do this in various ways. None of them quite, I think, achieve what is this set of desired properties. And I think the desired properties are being task dependent. So you extract features from the image knowing what you're doing it for, so you don't have to waste time in processing on things that don't matter. You probably need to do it iteratively. We know that the human visual system does it this way. It's much shallower than a typical neural network, but there are also a lot of recurring connections, and it takes longer. And so you run the image, you say, okay, based on what I've seen, let me look somewhere else, or maybe think some more about the features I've seen. You need to know when this process is done. And the big question is, why does it matter, and should we take any inspiration from this? I've had many arguments with some of you, including David and Michael, whether it makes sense or not. I have some arguments why it might make sense. We don't know, I think. Computers don't have to do everything the same way as people do, but I think there are some good arguments why this may be useful. And so I'm thinking about these things, kind of early stages of doing this work. I've convinced so far one person to work with me on that. I'm not going to say who that person is so that they don't get cold feet. And people have started thinking about this also in language to some degree. There is interesting work by, among other people, by Ari Holtzman, something called byte layer transformers, which tries to adapt the tokenization to the text, not necessarily to the task, but to the text. So just like, depending what image you're looking at, you should extract different features. But I think it's really not clear how to apply that. So I'll stop. If there are quick questions, I can probably do 1 or 2, and then we should wrap up. Right. Yeah.
So thinking of video as kind of a temporal object is sort of so roughly analogous to thinking of time domain representation of sound. Is there something which kind of also works with maybe a frequency or Fourier representation of video?
I mean, people have tried a lot. I always wish I knew more about Fourier transform. One of these days when I retired, I will. So I don't know. I mean, again, the point, I think the important point here is that some of the frequencies, there may be something which carries a lot of energy in high frequency, but you don't care about it. It's not important. It's not important at all, or not important to your task. And I don't know, I mean, maybe Karen has some thoughts about how it's done with sound processing. There's probably similar issues. There could be some noise in human reason. But I don't know of any successful application of that to these principles. And yeah.
Would somehow encoding the scale of time or space that a vector embedding represents in the embedding itself assist with some more universal vector embedding scheme versus these task-specific choices about the scale and kinds of objects that you're mapping into vectors?
It might. I guess I philosophically think that universal embedding is not right. There should not be universal embedding because I think that there's a trade-off that if embedding is universal, it either will have to be gigantic, which may be that may be okay, but I'd rather not do that, or it will necessarily cut some corners in a sense and lose some information. So I don't it's just not a direction I'm thinking about, but I think it's possible, and I know you are. So I think it's possible. And I think then you have to be prepared to pay the cost in very large embeddings. Yes.
In the case of image tokenization, as the real world is bounded by the geometry of the world, that is, so should we? Is there any point in considering that?
You mean 3D geometry? Yeah. It's complicated because 3D geometry is fundamentally ambiguous in an image, right? Image is 2D projection. In video, it gets a little bit more complicated. But also, while I didn't talk about this, there certainly are images which are not photorealistic images, and we still understand them, and we still can process them well. And those images are not subject to any geometry. So that makes me think that this inductive bias from 3D geometry probably is not the key. Maybe helpful in some practical applications. I don't think it has to be. All right, probably have time for one question, then I have to run. So, yes.
And how much would it make sense to learn contrastively with the language and the images?
I mean, that's what people do, of course, a lot today. I personally do not think that we should have to rely on text. And I know that David doesn't think we should rely on images, but
I have a long story, but it's too long for too long.
I think that text is a very what people say unreliable narration of the visual world. It's very limited. It's sometimes inaccurate. Attempting to do something about this isn't practical beyond this very small scale. So I think that may be helpful in practice, but probably should not be the key.
So you would disagree with Phil Isola?
I do disagree. Yeah, of course. Yeah. Where would be the fun without that? And I'm very excited to see how far he can push that. All right, I have to go. Thank you.